Okay, perfect. Yeah, people are coming in. Hello, everyone. Thanks so much for joining us for the Arua virtual seminar. I know this is especially busy time in the semester, so thanks so much for taking time and joining us for these great seminars. I am very pleased to have with us today Stijn van Nieuwerburgh from Columbia Business School, presenting his paper Understanding Rationality and Disagreement in House Price Expectations. Thank you, Stijn, for coming. You have 1 hour to present, and then we have a 15-minute Q&A session. I'm going to be looking at the chat and monitoring the chat for you, and I might interrupt you and tell you when you have questions lingering there. But feel free to defer some of those questions to the end if you need more time. And for the whole audience, feel free to unmute yourselves and ask questions if that's okay. Thank you so much for being here.
Great. Thank you, Luis. Thanks so much to all of you for attending. And as Luis said, feel free to interrupt with any thoughts or questions you have. Happy to take those along the way. So this is joint work with Zigang Li, who is a PhD student at Toronto Rotman, and Rengshuan Wang, who is an assistant professor in the SAPES in Shanghai. So in this paper, we want to study house price appreciation expectations, and specifically try to ask the question, to what extent can we think of those as being rationally formed, and can we understand this rationality as well as the disagreement in house price expectations, right? So this paper contributes to a very active literature on belief formation, not just in the housing market, but more generally, belief formation on all sorts of financial and macroeconomic variables. So what I thought I'd start with is with a picture which summarizes or highlights at least one very salient feature of these house price beliefs data that struck us right from the get-go. So the graph you're looking at here shows you this consensus forecast, which means the average forecast among a panel of forecasters of house price appreciation. And each of these little colored line segments tells us what the average forecaster thinks house price growth will be over the next 1 year, over the current calendar year, the next calendar year, up to 4 calendar years out, right? So you see from each point, for example, this point here, we have a whole segment of forecasts. And one thing that you notice is that no matter what the actual house price expectation is, which is what the solid line indicates, people are always pulling their longer run forecast back to the long run mean of house price growth, right? So this dotted line here is the long run forecast of house price growth. It's about 4% per year. And if you ask people what's going to be house price growth in 2026, they will tell you, basically the historical mean. So that's going to be one interesting feature of these data that we're going to want to explore, right? So let me tell you a little bit more about these data. These are a panel of forecasters, professional forecasters. They contain a bunch of folks from the traditional professional forecasters settings like investment banks. They also contain people, because it's real estate, from the real estate sector, construction firms, could be consultants, could be folks working at brokerage houses in the research groups. And they also contain a bunch of policymakers, people from the Fed, as well as some academics. In fact, I am one of the forecasters, as are several others among you, no doubt, filling out these quarterly forecasts of house price growth. And what we're forecasting here is national Zillow house price appreciation, okay? And we have access to the entire panel of these forecasts, right? So not just the consensus, but each individual forecaster, we know them by name, and we know which forecast they make each quarter for that entire term structure of forecasts, okay? And the forecast data begins in 2010. The actual Zillow actual house price time series, of course, starts earlier in 1996. Okay, and so that's a little bit about the data and some salient features of the data. So what I'd like to begin with in this paper, sort of the first thing this paper does is it establishes a bunch of new stylized facts about the term structure of individual forecasts as well as disagreement among forecasters. And I'd like to begin by running you through these stylized facts. And then after that, we're going to think about a model that could potentially explain these forecaster data. Okay, so the first important fact, and one that we think is crucial, and that we're going to emphasize throughout the talk, is this idea of individual forecaster overreaction and persistent biases. So let me show you what I mean by that, right? So in panel A of this table, what you're seeing is what's called the Koibian-Gorodnichenko regression. Okay, so basically, what is that regression about? It's about a forecaster gets new information. That new information leads him or her to revise their forecast. That's what's on the right-hand side. It's the revision in the forecast about house price growth 1 year ahead, 2 years ahead, 3 years ahead, whatever it may be. And on the left-hand side, we see the forecast error, the actual realization of the house price appreciation minus the forecast itself. And so what you're seeing for this regression slope, this Koibian-Gorodnichenko regression slope, BCG, is that it's consistently negative, and it's in fact becoming more negative at longer horizons. And what that's telling us is that when I receive a new piece of information as a forecaster, I tend to overdo it. I tend to basically revise my beliefs too much, so much so that the forecast error I'm making, which is the left-hand side, is actually going in the opposite direction as my forecast, right? So I think house price growth is going to be stronger than I thought last year, so I dramatically revise my forecast up, but I'm actually, overdoing it, okay? And that's what that negative sign means. This negative sign is something that people have found for all sorts of other macro and financial time series, and it's typically interpreted as essentially an overreaction, okay? And so very quickly you start to think this is a behavioral phenomenon, right?
Sorry, Stijn, one clarifying question. Whenever you say you overdo it, that is with respect to the realization, to the real prices, or to your own previous forecast?
With respect, so you're making a forecast. Your new forecast is systematic. Let's say that you thought that let's say that you got positive news about house price growth, so you revise your forecast up. You're revising it up more than the actual realization will come in on average. Okay, Andrea.
Yeah.
Go ahead.
Good to see you. Yeah, so I'm one of these pulse-odomics forecasters, and I, knowing they don't pay me for my forecast, that it is, service or maybe for the glory. So I'm wondering if you saw this. The reason I say this is that, how much time I would spend on my forecast if they actually paid me versus how much time I actually spent. Do you think that the fact you're looking, I don't know whether other people on the panel are paid or but that is a concern I have. And I don't know if this anomaly would hold as much if I were paid.
Look, we don't know. I am just for clarity, I am also not getting paid for this. And I suspect that nobody on the panel is. I think that same issue, though, arises in all sorts of professional forecasts, including all the big inflation and interest rate forecasts that we spend so much time studying and researching, right? So, I think incentives are interesting to consider. Maybe my incentives are related to, in the context of let's say a Wall Street firm, to the transaction volumes that may be associated with that potentially could cause my forecasts maybe to be biased in one way or another. I'm not sure I know there's a couple of papers that have thought about incentives for forecasters to make certain types of forecasts. I think if it's all just we're not spending enough time, there's no reason to believe that the forecast, that's sort of classical measurement error. There's no reason to believe that the forecast should be biased one way or another, or these regression slopes should be, of one sign or another. So as long as it's just classical measurement error, I don't think it's necessarily a problem for us. So let me tell you a little bit about a second anomaly. So the second anomaly is what's called the Mincer-Zarnowitz regression coefficients. So this is all about how responsive is the forecast to the actual realization. And in a full information rational expectations model, the forecast should move 1-for-1 with the realization, right? So if you regress the forecast on the realization, you should find a coefficient of 1. Not only do we not find 1, we're finding something strictly smaller than 1 at every horizon, and in fact, sometimes even close to 0 at longer horizons, right? So this, again, looks like prima facie evidence of deviations from full information rational expectations. And then the third anomaly is the bias, the forecast bias. So on average, is the realization higher or lower than the forecast? And in the data sample that we have, we see substantial positive bias, which means that the house price realizations, house price growth realizations come in much higher than the forecast at longer horizons, as much as 4% per year, 4 percentage points higher house price growth than the forecast. Okay, so systematically biased forecasts, right? So these are going to be 3 sets of moments, especially we're going to be focused especially on the first one, but all of these moments, we're going to try to explain those with our model. So these are, think of these as features of the forecast that we're going to try to wrap our mind around. Okay.
You have one question from
Yes.
Sudan. You wanna unmute yourself?
Yeah, sure. It's not. I assume there's heterogeneity in terms of familiarity with the real estate industry among the forecasters, right? I assume you're going to get to this, but I wonder how much of this is driven by people further away from the industry being, less familiar with what's going on in the real estate market.
Yeah, it's a good question, Sudang. Thank you. We're going to spend quite a bit of time thinking about this forecaster heterogeneity along a series of dimensions. We actually spent a ton of time trying to map each and every one of these forecasters to their LinkedIn profile and get their entire background and their history and their education and their experience. And I'll show you some results relating to that. But just sort of as from the get-go, these are all experts. Okay, so they're all, I think none of them are very far from real estate. It's not like, we have, they're all experts in the real estate market, but I'm sure there's some heterogeneity in their degree of expertise, right? And we'll come back to that.
Gotcha,
So,
thanks.
So the second set of moments that we're going to want to come to grips with is what we think is very interesting is that forecasters tend to under-extrapolate. So from recent house price growth, right? So let me tell you what I mean by that. Let me show you what I mean by that. So I'm thinking about to what extent does my forecast depend on lagged realized house price growth? So if I just experienced a lot of house price growth in the data, does that lead me to forecast higher house price growth? And the answer is yes, it does. That's what the blue bars show, right? So the blue bars show you the regression coefficient of my forecast on lagged house price growth. In the left panel, it's lagged 1-year house price growth. In the right panel, it's lagged 4-year house price growth, okay, over the last 4 years cumulatively. And you can see all of these blue bars are positive, meaning, I'm attaching some weight, I'm increasing my forecast if past house price growth was high, okay? So so this is, again, a fact that we also know from other survey evidence in other contexts. But what's special about house prices is that unlike stock returns, for example, house price growth, capital gains in the housing market are actually very persistent themselves, right? So it's not because we're loading, it's not because these forecasts are loading on past house price growth that they're over extrapolating. In fact, what we're finding is that these forecasters are under extrapolating from the past, right? If you actually regress the realized house price growth on the same lags of house price growth, which is what the green bars show, you see that the green bars are higher than the blue bars, okay? In other words, house price growth, and we all know this, house price growth is persistent, unlike stock returns, which are not persistent. House price growth is persistent, and when forecasters are thinking about that persistence, they're actually under extrapolating. They should have their forecast load more on lagged house price growth than what we see in the forecast data. Okay, so that's a second set of moments. So we have sort of simultaneously this overreaction to new information from the Koibian-Gorotnichenko regressions and this under extrapolation from past realized house price growth. And then the third set of moments we're going to want to think about is disagreement across these forecasters, right? So these are all professional forecasters, but they actually have major disagreements about house price growth. And again, let me illustrate this with a chart. So this is the last data point we have. This is just a representative data point in our sample. It's the last quarter of 2023. And in that forecast, the forecasters are asked, what do you think house price growth will be in calendar year 2024, in calendar year 2025, in calendar year 2026, and in calendar year 2027? And then, so I'm showing you 2 of these, calendar year 2024 forecast and the calendar year 2027 forecast. And right away, what you notice is that the dispersion, the disagreement across these forecasters is much larger for the next year's forecast than it is for the long horizon forecast. And this again is a pattern that we see sort of throughout the different surveys. There's a lot of disagreement. First of all, think about this. Some people think house price growth is going to be negative 10%. Other people think it's going to be plus 10%. That's a massive amount of disagreement. And that disagreement tends to shrink with the forecast horizon. Okay, so that's a third set of moments we're going to want to come to grips with in the context of a model. So these are I think some new features about house price forecast data, that some of which I think we knew, some of which I think are new, that we're going to want to try to explain with a model. And so the model we're going to put forward is essentially a fairly standard rational Bayesian learning model. So it's not a full information rational expectations model, because we're going to assume that people do not know the state of the housing market. They do also not know the parameters that govern the state of the housing market, right? So we're basically, the deviation from rationality here comes from just a lack of knowledge of the parameters and the state that drive the housing market. But people are rational in the sense that they're doing the best they can to, learn as much as they can about these parameters and about the state from past house price growth, as well as from other signals that they may get about the housing market. Okay. There's a question here. Amin?
Hi, Stijn. Yes, I was wondering whether it's possible to say that they're uncertain about policies such as monetary policy. I mean, we know that the next 6 months are going to be depending on monetary policy decisions in terms of rate cuts. And I was wondering whether here we have a strictly within the housing market view, or whether you want to connect the uncertainty in the housing market with the uncertainty about other parameters of the economy. If I think about a DSG model, housing is going to be one component of that VAR, right?
Yeah, very good question. So the way we're going to think about that question is we're going to have signals that these forecasters all receive. And these signals could be different for different forecasters. And they could, for example, reflect different views on monetary policy or different information that these different types of forecasters get about monetary policy. So that's the sense in which we're going to incorporate this. One of the issues that we have to do this more formally is that we do not know any other forecasts from these forecasters, right? These forecasters are only forecasting house price growth. It's not like we also see their inflation forecast and their interest rate forecast. We don't have that data. So that's going to force us to take a housing view, right? But you could think of this as indirectly being filtered through the information, the signals that these forecasters are getting. Okay.
I think there's a related question to what you're presenting from Joshua Abel. Like, do you want to unmute yourself and ask it, or else I can read it?
Yeah, I guess I'm just wondering if there's any issues here with like data vintages where you're evaluating this stuff with, I assume the up-to-date Zillow home price index, but if it's subject to revisions, they may be getting different readings when they're making forecasts.
No, we know that's not an issue here, because we know what the house price history was at the time of the forecast, right? So the forecasters are shown past house price growth in the last 3 or 4 years when they make the forecast. So they see a screen, and the screen has, here's what house price growth was in each of the last 3 years. So everybody sees the same information, and it's the information that was available at the time. So we're not using any forward-looking or revised Zillow data.
Okay, got it. Thanks.
So so the learning is about both the parameters, that's going to be new and important, as well as about the state of the housing market. Okay, and then we're going to have heterogeneity across these forecasters, both in terms of the signals, the information that they're receiving, and also their prior beliefs about these parameters. Later in the talk, so I'm gonna use this rational model as my benchmark, and it's not because I am dogmatic about a rational framework. It's just because we want to ask the question: how far can we go with a rational framework? We're gonna show that the rational framework goes a long way towards explaining these stylized facts that I just shown you, but not all the way, which means that there will be scope for behavioral frictions, and we'll talk about a couple of different behavioral frictions. One is overconfidence, the other one is diagnostic expectations, which will essentially help close the gap between the rational model and the data. There'll be a couple of moments of these many moments I presented you that are not well accounted for by the rational model. And it's exactly those couple of moments that the behavioral frictions will be very helpful to match. Okay, so at the end of the day, we'll get sort of a nuanced picture where the rational model gets you a long way, but not all the way, as well as the rational model is going to be very good at matching the longer horizon forecast, whereas the behavioral model will be very useful for fixing some of the issues with the shorter horizon forecasts and the shorter horizon dispersion. Okay, but we'll come back to that. And then we'll also ask, to what extent is the heterogeneity in these forecasts, this dispersion in the forecast, driven by informational heterogeneity? So in other words, differences in signals that different people get versus prior information, prior heterogeneity. Okay. And then the last thing we will do is, once I've sort of convinced you that this uncertainty mechanism, and in particular this idea of uncertainty about the long run mean of house price growth, that's going to be the key mechanism in the paper, uncertainty about the long run mean in house price growth. Once I've convinced you that that's an important feature of the data, there's uncertainty about that parameter, the long run growth of house prices, is driving our results. I'm going to try to show you some micro data from the forecasters where I'm going to be using their, all the interesting, micro level evidence on the characteristics of these forecasters that we have here to build support for that learning story, to build some direct evidence, give you some direct evidence for that learning story. Okay, so let's get a little bit more into the model. So the model is actually simple yet complicated. It's a richer model than what is in the beliefs literature. For example, the Farmer, Nakamura, and Steinson paper in the JPE a couple of years ago, as well as the Bordalo, Schleifer et al. Paper in the AER from a couple of years ago. So our model nests both of these models as special cases. So in that sense, it's a richer model. It's also still a very simple model because at the end of the day, it's a time series model for house price appreciation, right? So it's sort of a mechanical model. There's no choices being made here, no optimizing behavior. We are just positing a time series process for house price growth and trying to estimate the parameters of that process, okay? So house price appreciation, Y, it has a long run mean, mu bar, right? So that's the parameter. That's going to be the key parameter here. Okay, so this is the true data generating process, which nobody in the world knows. But it's generating the data. So mu bar is the long run mean of house price growth. Then there's this persistent component to house price growth. Think of that as the state of the housing market. And again, that could be driven by monetary policy, by the construction sector, by interest rates, what have you. So that is persistent with some persistent parameter rho bar. And then we have both shocks to that, to the transitory component and to the persistent component of house price growth. The relative importance of these shocks is governed by the parameter gamma, and then the volatility of house price growth is governed by the parameter sigma. Okay, so all the parameters that have a bar over them are the true parameters, which again we do not know. We need the agents in the model need to learn about. That's basically the data generating process. Okay, so it's a simple model, a simple stochastic model of house price appreciation. So the key friction here is that the forecasters do not know the parameters of the model. They do not know mu bar, rho bar, gamma bar, and sigma bar. They need to learn about them. They also do not know the state of the housing market. This is a latent state, X. Okay, and again, they need to filter back that state from observed data. So what data do people have? Well, first of all, every forecaster gets to see the history of past house price appreciation, and there's no disagreement on that. And again, that just reflects the way the survey is presented to the forecasters. They get presented with what past house price growth was. Okay, so we all agree on past house price growth. What we don't know is where we differ in the first key difference across forecasters is the signals, the other sources of information that we bring to bear on this forecast. Right, so these forecasters are getting heterogeneous signals S about the current quarter's house price growth. Let's call it Y capital T. And on average, these signals are unbiased. So on average, these signals are equal to the truth, but there is some noise around these signals, and that noise is governed by this parameter gamma. Okay, so gamma is going to be the perceived signal precision that these forecasters have. Okay, the noise in the signal, the perceived signal noise level. And in a rational model, the true signal precision is equal to the perceived signal precision. Later, when I return to the behavioral models and I talk about overconfidence, that's when I'm overconfident, my perceived signal precision is higher than the actual signal precision. That's going to be the way we're going to model overconfidence. Okay, but for now, the true signal precision is the perceived signal precision. The second place in which these forecasters differ is in their priors. Okay, and in particular, we're going to allow these priors to be heterogeneous in one dimension, namely the prior about the long-run mean house price growth. That's going to be the key parameter that we learn about. We're going to argue it's very hard to learn about long-run mean growth, and that allows for there to be a lot of initial disagreement about what that long-run mean parameter is. So we're going to assume that these different forecasters have a different prior mean belief about long-run house price growth, mu mu, that is centered around some parameter mu mu, with some cross-sectional dispersion across forecasters governed by this parameter lambda. Right? So if lambda is large, then I will have very different prior beliefs about long-run mean house price growth than Andra does. Okay, and that heterogeneity we're going to show is going to be very important to help explain the dispersion across these forecasters. So that's basically the model. At that point, it becomes a Bayesian learning model where each of the forecasters is using Bayes' law to update the parameters and the state based on their heterogeneous information, starting from their heterogeneous priors. All the other priors about the other parameters, about rho bar, about sigma bar, all of those are common across forecasters. And so then we're basically going to observe, we're going to run through time. These forecasters are going to run through time. They're going to see the realized house price growth, and they're going to update their beliefs about the mean, the long-run mean house price growth, the persistence of house price growth, the volatility of house price growth, and how much of the shocks are temporary versus persistent. Okay, and because we all get different signals, all of these posterior beliefs are going to be individual specific and time varying. Okay, so this model, even though this model will generate, even though the parameters are not time varying, this model will generate time varying posterior beliefs as well as heterogeneous posteriors. And we're also going to end up with a posterior belief on the state of the housing market, X tilde, using a Kalman filter and Kalman smoother. So then, yeah, go ahead.
There's two sources of heterogeneity across forecasters, right? So they have heterogeneous priors, but if you could go back to the previous slide, yeah, so their perceived signal precision equals the true, but is it the same across forecasters, or some have different signal precision?
So the signal precision is going to be the same, but of course we're going to get different draws from that, right? So we're going to all have different signals, and that's a very important source of heterogeneity, right? So you will have different information than me, but it's drawn from the same distribution. Okay, so it's not like you have systematically more precise signals than I do.
Got it.
Okay,
I thought you were, when you mentioned that you had like micro data about the forecaster's experience, I thought that was where it was going to play a role of having a smaller noise in the interpretation of the data.
So we can come back to this. Is a good question, but what we will show is that there will be, so this model, even under this assumption of homogeneity on the parameters, will generate behavior that looks exposed, like there's differences across, and that's considered, and in the model it will be exposed differences across these forecasters and how good their forecasts are, right? So you can generate that even with homogeneous parameters. Okay, and so then at the end of the day, what the model puts out is what we're interested in, which is this forecast, right? So the model will predict a forecast of future house price growth for every horizon age, this calendar year, next calendar year, the calendar year after that, which is equal to my posterior long-run mean of house price growth, plus my posterior persistence of the latent state raised to the power h for the forecast horizon times my perceived state of the housing market. Okay, and all these things are time varying and individual specific. So this model will generate a panel of forecasts that differ across horizons as well, across the term structure, as well as across panelists. Gary.
Yeah, so housing price appreciation in the theoretical model, obviously that's uniform for all of the forecasters, meaning they're thinking about the same exact measure of housing price appreciation, whether that's appreciation on repeat sales or whether that's appreciation over particular geographic units or national level, that type of thing. But when it comes to the micro data about the forecasters, and I might have missed this earlier, and I apologize, I came like 2 minutes late. Are all of the forecasters predicting the same measure of housing price appreciation, and are they all aware of the intricacies of that measure of housing price appreciation? So I guess what I'm saying is the model is reflective of a state where everybody knows exactly what they're supposed to be predicting. Is that reflected in the microdata?
I think so, in the sense that it's very clear what the object is that the forecasters are supposed to predict. They're all supposed to predict the exact same object, which is in the National Zillow House Price Index. I think they are given, when they first sign on to make these predictions, they're given a methodology, the way the Zillow Index is produced. To what extent do they all understand the intricacies of that? That is a good question. There's no way to verify that, I think. But yes. Now, I think where you're steering at is sort of an interesting possibility, which is that maybe people are getting different signals based on where they live about the national house price growth, right? Now, the model can accommodate that in the sense of, that's your signal versus my signal. If you're in Atlanta and I'm in New York City, maybe I get different signals about the state of the housing market that lead me to change that make my beliefs about the national house price index different from yours. And that's the model allows for that through these signals, right? I think there's potentially interesting things to be done with sort of studying that a little bit more in detail, because we actually know where these forecasters live.
So that was actually my follow-up to that is, are you going to include a measure of geographic dispersion of forecasters? Because it might be the case that many of your forecasters are, say, in a high growth area, and their forecasts are biased because they're used to seeing high house price appreciation.
We're not going to do that, but I think there's sort of a next paper that pushes in that direction. I do agree with you that that's sort of an interesting direction to go. Okay, so where are we at? So I've given you these sets of moments that we're going to try to explain, which have to do with the term structure of individual forecasts as well as with disagreement across these empirical moments. And I've given you a simple model that has essentially 6 parameters. And so we're going to do a simulated method of moments estimation, where we're going to try to estimate the 6 parameters in the model. Let me run through them one more time. So we have the prior about the long run mean growth rate, which we're going to assume is normally distributed. So there's this prior mean and prior variance about long run mean growth. We have similarly a normally distributed prior belief about the persistence parameter, rho bar, again, the prior mean mu rho and the variance sigma square rho. And then we have these 2 sources of heterogeneity: signal heterogeneity, what's the signal precision, and this prior heterogeneity about that mu mu. Remember, this mu mu differs across forecasters, and the range of those mu mu's is governed by this parameter lambda. Okay, so those are our 6 parameters that we're going to estimate, and we're going to estimate them to best match these 36 empirical moments that I showed you at the beginning of the talk, right? So just to remind you, the forecast bias at 4 different horizons, the Koibian-Goretnichenko regression coefficient at 4 different horizons, both the intercept and the slope of those regressions, the Mincer-Zarnovich intercept and slope at 4 horizons, and then these regressions where we regress forecasts on lagged realizations of house price growth. And we can do that again for 4 different horizons and with 3 different lags, so that gives us 12 more moments. And then finally, the dispersion across forecasters at each forecast horizon. Okay, so those are the 36 moments. We're going to estimate 6 parameters to match these 36 moments. So this is an over-identified system. This is actually a very computationally heavy task. We do this on Microsoft Azure cloud computing. We sort of spent years trying to estimate this model, but I think we have this down now. Okay, so first thing I want to do is to show you that model fits the data well, that it fits these 36 moments, and talk a little bit about the parameter estimates that we get, right? So the way you should think of this is we're going to initialize this model in 1996. Why 1996? That's when Zillow house price data became first available. And so you should think of the prior as applying to 1996, right? So the question is, what were the forecasters thinking in 1996? What were their prior beliefs about mean house price growth? And so the model estimates that the center of the prior distribution is 0.66% quarterly house price appreciation. So these are quarterly appreciation rates. So about 2.5%, 3% per year annual house price appreciation. That's the center of the prior distribution about long-run mean house price growth. Interestingly, that lines up very nicely with average house price appreciation according to the Case-Shiller house price index, which is available a little bit before 1996, which was 0.69% per quarter. Okay, so that seems like a reasonable number. Second, and this is the key part of the paper, this parameter sigma mu is very high. So there's a lot of uncertainty about that long run mean. Okay, and I'm going to argue how we identify that. Where does that estimate come from? Because that will be the key to the paper, is this 0.18. Okay. Third, also important, is there's enormous amount of heterogeneity about this mean, this long run mean house price growth. Okay, people have very different priors about this long run mean house price growth. Okay.
Sorry, Stijn, sorry to interrupt. There's two questions in the chat, one by Kundan and another one by Andra. You guys want to mute yourselves?
Sure, I can, sure, you said this, I'm sure that I missed it. This is nominal, correct, Stijn? It's not
Yes,
real
yes, this is all
appreciation.
nominal. Yeah.
Yeah, one thing I personally have experienced in doing these forecasts, and it's probably less relevant for 1996, a lot of what I'm trying to do is also figure out what the rate of inflation is. So I have in my head what I think the real rate of house price appreciation is, and then I'm like, what's inflation going to be in the next 2 years or 3 years? So it might just be worth thinking about kind of disentangling those two things, given that the questions ask about nominal appreciation.
Yeah, but again, we don't have any data on inflation forecasts, right? If we collected your inflation forecast, I agree that would be a very useful thing to do.
Sure,
to try
fair
to
enough, yeah.
understand that, but we have sort of no way to discipline
Of course.
that separation.
Kundan?
Yeah, I have a question, like two quick questions. Are these forecasts, do we have information if these are model based or judgmental? Because model based will have a tendency to move towards, long run. If it is stationary, it will converge to its long run mean. But if it is judgmental, there may be,
We don't know. We don't know what they are. My own forecast, and again, that's just one data point. I've shifted from essentially a mental forecast in your language to a model-based forecast, right? So I run a battery of machine learning models every quarter, and then pick the one that I think makes most sense. So there's some sort of machine learning ensemble model averaging in the background of my forecast, but I'm sure everybody is different.
And you are also assuming that this lambda parameter is time invariant?
All parameters are time invariant. But again, the posterior beliefs will be time varying. Okay.
Okay.
This is about the prior. These are parameters about the prior. All posteriors will be time varying and individual specific. Because we all get different information. So over time, our forecasts begin to evolve differently from one another.
Well, thank you.
Any other questions? Okay, so then turning to the persistence parameter. So this we thought was also interesting. The persistence of the latent state of the housing market is 0.67 quarterly. So that's not very persistent. And that's in fact, much less persistent than you might have thought this could be. So this is really not about long run growth or anything like that. It's really a cyclical. This is really a cyclical variable with this type of persistence, right? And interestingly, the prior dispersion, the prior uncertainty about that parameter is very, very small, right? So people's priors are very tight around that persistence. They think the persistence is 0.668 per quarter with a very tight prior around it. Okay, what that will mean is that there's going to be very little learning about the persistence because we think we know what that number is. Okay, so that's going to be interesting. It's going to allow me to differentiate our paper from the Nakamura, Steinson, and Farmer paper, which is all about this persistence parameter. We'll come back to that. And then finally, we have a lot of information heterogeneity as well. This is about the signal dispersion. So we have both a lot of prior heterogeneity and a lot of signal heterogeneity. And so it's a question of how much of each do we need in order to explain the dispersion in house price growth. Okay, so now let me show you these 36 moments and how well the model matches them. So each bar is going to be one of these 36 moments. There's a couple of slides here. So the first one is the Koibian-Gorotnichenko regression coefficients, right? Remember, these were like very negative numbers in the data, suggesting this, this overreaction to new information. The model can match that quite well, except at the 1-year horizon. Okay, and so this is a first moment that that we're going to call a miss for the rational learning model, and this is a first place where the behavioral frictions will be helpful later down the line. Okay, these Mincer-Zarnowitz regression coefficients, remember, that's about the responsiveness of forecasts to realizations, that 1-for-1 relationship in a full information rational expectations model. We are very far from one, both in the model and in the data. The forecast bias, the model generates the fact that these forecasters are under-predicting on average the forecasts in our sample from 2010 to 2020, end of 23, by about the right magnitude. Then we have the sensitivity of the forecasts to lagged realizations. So I showed you the blue and the green bars before. Now I'm showing you the orange bars as well. The orange bars, you should compare them to the blue bars. They're the model's prediction about the relationship between the forecast and lagged realizations of house price growth. And again, the blue and the orange bars are pretty close to each other. So the model can replicate the fact that in the data, the forecasters seem to under-extrapolate from past house price growth. And then finally, the forecast dispersion, the cross-sectional dispersion across forecasters at different horizons. Again, the model does a good job generating a lot of forecast dispersion, again, especially at longer horizons, 2, 3, and 4. It does underpredict the forecast dispersion at the short horizon relative to the data. So the model struggles to generate enough dispersion across these forecasters at the 1-year horizon. This is the second moment out of the 36 where the rational learning model struggles. And it's the second place where the behavioral frictions will be helpful to close the gap between the model and the data, right? So sort of the conclusion that we take from this is that these 36 moments, we can basically match 34 of the 36 with a rational learning model. There's 2 moments where we struggle: the short horizon Koibian-Gorotnichenko regression slope, which is about overreaction to news, and the short horizon dispersion of the forecast. Okay, and both of these I'm going to show you we can fix with one of 2 behavioral frictions. The other thing, yes, question.
I understand this as saying that a lot of the quote unquote puzzling moments that we saw in the forecast can be explained by the rational model. Is the rational model in this explanation kind of a black box? Like it
No, I'm going to give you intuition for that. That's coming up.
Okay.
That's coming up in 1 minute. So I'll explain why we find this, okay, and why this makes sense. So the last thing I want to show you from the model output is the graph I started my talk with, but now the same graph in the model, right? So remember I pointed out that forecasters on average, the consensus forecast, the average forecast gets pulled towards the mean in the longer run. The model generates exactly this behavior, right? So this graph looks a lot like the graph that I showed you at the beginning of the talk. And you know, that's sort of another fit. So in the paper, we spend more time talking about over-identifying restrictions. There's a lot of other moments that, remember, we had 36 moments, only 6 parameters. So there's over-identifying restrictions. We show other moments that the model matches, one of which is a switch in sign in the Koibian-Gorotnichenko regression slope, whether you look at individual forecaster data or consensus forecast data. Okay, I'm going to skip this in the interest of time, but there's several other moments in the paper that we describe where we show that the model fits the additional features of the data, not targeted in the estimation. So let me spend some time on explaining why this works, okay? And then also compare with an alternative mechanism. And in the process, essentially what I'm going to be doing is describing how we identify the parameters, right? So this is, I think, these moments are actually going to be providing very tight parameter identification, and I'm going to hopefully give you some intuition for why. So the key thing in the paper is about learning about the long run mean, right? And so that's going to generate overreaction and extrapolation. So let's begin with a benchmark. A benchmark is a full information rational expectations model, right? Where everybody knows the parameters and the state of the economy. In that world, the forecasters are going to stick to the true value of these parameters, which they know, and they're not going to revise their forecast about long-run mean house price growth, right? So in our explanation, investors or forecasters do not know the parameters of the model, and they're going to need to learn from data, okay? And so this overreaction and extrapolation are going to result from imperfect information. So again, forecasters do not know the true long-run house price growth, right? So they're and so they need to learn about it. They need to make inference about it, combining their prior beliefs and the signals that they get, right? And so they're perceptive about new information. They're going to put some weight on the signal. So they're going to get a signal and they're going to revise with the data, with the signal, following Bayes' rule. And if the uncertainty about their prior is large enough, in other words, if they're not dogmatic, if they're not saying, I know what the long run mean is, if they're open to the idea that data matter to have them revise their forecast, sigma mu is large enough, then essentially when they see positive news, they're going to update their posterior belief in the direction of that news. And relative to a full information rational expectation model, that's going to look like overreaction. Because remember, if I'm a dogmatic forecaster, if I know the truth, or even if I'm close to thinking that I know the truth, then I'm not going to revise my forecast very much, right? So to the econometrician, when you run the Koibian-Goretnichenko regression, you're going to estimate a negative slope in this model. It's going to feel like it's behavioral. Somehow people are overreacting, but in fact, they're doing the right thing in a world where they don't know the truth and they're trying to learn and they're putting some weight on the data that they're getting. And they're revising their beliefs, their posteriors in the direction of the data and therefore their forecast in the direction of the data. Okay, so to illustrate this, what you can do is you can vary this parameter sigma mu, this uncertainty about the long run mean. And you should think of a very low value for sigma mu as essentially a dogmatic prior, where I know the true long run mean, and a very high value as I'm very, very uncertain about the prior, so I'm going to put a lot of weight on the signal, right? So our benchmark estimate is 0.18, which is this line here, and you can see at this benchmark estimate, we are generating negative slopes for the Koibian-Goretnichenko regression. So what this graph illustrates is that if I'm not uncertain enough about the prior, then the sign on this Koibian-Goretnichenko slope will actually be positive instead of negative, right? So this tells us, that this is a moment that is telling us that we're going to need, if we want to match the negative slopes that we see in the data for the Koibian-Goretnichenko regressions, we're going to need sigma mu to be large enough. Okay, so that's sort of the first. It's bounding our sigma mu parameter away from 0 towards a high enough value. It cannot, we show that it cannot be too high for a couple of reasons. One of which is that if it becomes too high, if sigma mu becomes too high, I end up over extrapolating from the data. The second reason it cannot be too high is because the forecast dispersion is telling us it can be, right? So remember, we have a lot of forecast dispersion in the data, a lot of disagreement across these forecasters, right? And what that's telling us is that this prior uncertainty cannot be too high, because if it's very, very high, then forecasters are basically going to say, look, I have no idea what long run mean is. I'm going to really rely solely on the data, on my signal. And then we're all going to get a lot of signals. We're going to put a lot of weight on these signals. We're going to very quickly converge to the truth based on the signals. And so what that's telling us is that sigma mu cannot be too high, because if it was too high, again, we would very quickly, there would be very little residual dispersion in our forecast after a while. Okay, and so basically putting these two things together, on the one hand, sigma mu cannot be too low. That's what we learned from the Koibian-Goretnichenko regressions. On the other hand, sigma mu cannot be too high. Otherwise, we cannot generate enough forecast dispersion. So these two sets of moments are tightly identifying sigma mu to be in some intermediate range, and a range in which learning about the long run mean matters, right? Where there's a lot of uncertainty about the long run mean. A lot, but not too much. Okay, so I think that's sort of the heuristic intuition for parameter identification about this key channel in the model, which is learning about the long run mean. Okay, now you can show another way of thinking about this is that you can solve a special case of the model where you pretend that you don't have cross-sectional forecast data. You pretend that you only see consensus forecasts, which, by the way, is the case in many surveys. In many surveys, all we have is a consensus forecast, an average forecast. And in that world, if you estimate that model, that special case of our model, where you basically throw away the individual forecasts and you only give the estimation the consensus forecast, then you end up estimating a much lower sigma mu, in which case essentially that learning about the long run mean mechanism is shut down. And that model, first of all, fits the data a lot more poorly. But more importantly, it suggests that it's really important to observe individual forecasts, when you're going to do inference on the parameters. It's very important to have that panel dimension. Jonathan.
Yeah, hi. So a lot of this, I guess, inference based on the dispersion of forecasts is, I guess, based on the mean dispersion over time. So, but there should be, I mean, your model predicts there should be changes in dispersion of forecasts over time. Or do you see that in the data?
We do, and I'm going to exploit that to some extent in a little bit when maybe coming up right now, actually. So let me see whether this answers your question. Okay, so in the interest of time, you know what I'm going to do? I'm going to skip this part. So the paper has a long discussion about how our mechanism, learning about the long-run mean, differs from the Farmer, Nakamura, and Stijn GP mechanism, which is all about biased prior beliefs about the persistence parameter rho. And long story short, if you have upward bias, if people think that the persistence about the state of the economy is higher than it truly is, then that can also generate negative Koibian-Gartnichenko regression slopes, but only at the expense of generating too much extrapolation, too much responsiveness of forecast to lagged house price growth. So I'll refer you to the paper for that discussion. Okay, so now let me come back to Jonathan's question and more generally try to provide some supporting evidence for this learning mechanism. Is there anything in the data that sort of provides direct support for the fact that these forecasters are learning? And we think that there is. In fact, we present 4 pieces of evidence from the individual forecast data that are consistent with the model. So in the model, learning is very slow because learning about the long run mean is very hard. And these priors are very heterogeneous. That's that lambda parameter, right? Our priors about the long run mean are very different one from another. What that means is that the individual's forecast errors should be very persistent in the model, right? They are persistent in the model. They should also be persistent in the data. And the question is, are they persistent in the data? In the model, they are. And are they equally persistent in the model and in the data? And the answer is yes. Okay, so in this model, forecasters are making persistent forecast errors. And that persistence of the forecast error, whether it's the forecast error itself or the absolute value of the forecast error, is similar in model and data. So that gives us sort of direct evidence for the slow learning and the large amount of heterogeneity in the prior, which, because learning is slow, translates into heterogeneity into the posterior. The second thing that the model predicts is that the forecast disagreement is driven by these prior beliefs. And what that should mean is that the dispersions in an individual's long-run forecast should be very large. Okay, and again, that's what we see in the data. So this is data. The solid line is the median forecaster. And then the 2 dashed lines are the 5th percentile of the forecaster's distribution and the 95th percentile. And so what I need you to see is that this range between the 5th and the 95th percentile is very, very large. In other words, there is not much convergence over time. So this is, I think, Jonathan, in answer to your question, this disagreement is basically persisting over time. It does evolve over time, but it doesn't really converge, for example. Right, and so it's staying very high and very low and for a very long time, which again is consistent with what happens in the model and suggests that learning indeed is slow and that there's a lot of disagreement. So that again is sort of direct support for our mechanism. And then finally, oh, by the way, the third piece of evidence is that the dispersion in the long run forecast should go down with your experience level. If you've been forecasting for a long time, you've learned for a longer period of time, and if I look at all the people who've been forecasting for 20 years and I compare that with all the forecasters who've only been forecasting for 1 year, I should see that the first group has smaller dispersion than the latter group, and that's exactly what we see in the data. And then finally, my favorite piece of evidence is this last piece here, which is that individuals' forecasts should evolve as they learn. And so these individual forecast errors should vary with the amount of experience that you have. Okay, and so that's what we find. In fact, like I pointed out, we match each and every one of these forecasters through their LinkedIn profile, with their educational background. Are they a STEM major? Are they economics? Where do they work? Are they professionals? Are they academics? Are they policymakers? All of the above. Where do they live? So there's a whole slew of forecaster characteristics that we collect. And then we regress their forecasts on these characteristics, as well as their forecast errors on these characteristics. And none of these characteristics matter except for except for their length of professional experience. Okay, there's a full table in the paper. I've omitted all the other characteristics. None of them are significant except for length of experience. So people who've had very long careers, more than 35 years careers, they have systematically lower forecast errors than the people who've been forecasting for a shorter period of time. And in fact, this is a monotonic relationship where my forecast error is going down and down and down the longer I've been forecasting. Okay, so that's in the data. That's sort of prima facie evidence for a learning story, we think. And in fact, we go a step further and we ask, can the model generate a pattern like this? So we literally take every forecaster that we see in the data, when they enter, when they exit from the panel, we endow them. So we know their career, we know how long their career is, we know when their career starts. So we know Andrea graduated from the PhD in this year, so we know when she enters the panel, so we know how long her professional experiences, and then we endow her at the beginning of her professional career with prior beliefs that are based Malmendier-Nagel style on all the house price growth that she's experienced over her life since her birth, okay, with a declining weight. So we sort of really mimic, we have a sort of a mental model for where the priors come from. They come from past lived experience. And we match the exact length of experience for each forecaster, as well as the exact timing of when they enter and when they exit the forecast. And then we let them learn in the model. And then we run the exact same regression that we regress here in the data. Okay. And we basically find that the model generates that same relationship between forecast error and experience. Okay, so that model, which is this learning model, is basically fully consistent with what we see in the data. Where basically, when people have been learning for a longer time, they're closer to the truth in terms of their parameters and the state of the housing cycle, and they make smaller forecast errors. Okay, so we think all this evidence, I think, bolsters the story for learning. So the last thing I want to do is come back to these two moments that the model missed, and in that context discuss or study two behavioral frictions. One is diagnostic expectations, a la Bordalo, Gennaioli, Laporta, and Schleifer, which you could think of as basically people are they're not using the common filter, they're using a distorted filter, and that weighs recent experience more heavily. And this diagnostic filter has one parameter, theta, and you could think of theta 0 as basically a special case of diagnostic expectations that recovers the rational model, the rational learning model. And then if theta is high, is positive, then people are sort of putting more weight on recent evidence. So Schleifer, in their papers, which are not about housing but about other forecasts, they favor a value of theta around 0.8. Well, it turns out as you increase theta, the forecast, the slope of the Koibian-Gorotnichenko regression at the 1-year horizon becomes more and more, it starts to go down, and in fact, at some point becomes negative, and in fact, it's close to the data for theta of 0.8. So that was, remember, the first moment that the model missed. The second moment that the model missed was this short horizon forecast dispersion across forecasters at the 1-year horizon. And again, that goes up monotonically and strongly with that diagnostic expectation parameter. And again, for a value of 0.8, the model is actually close to the data. So both of these moments, the 1-year CG coefficient and the 1-year cross-sectional dispersion are now also matched with the addition of the diagnostic expectations. Importantly, diagnostic expectations leaves the longer horizon moments unaffected. Okay. And so it doesn't really, as you can see, it doesn't really affect these 2-year, 3-year, and 4-year Koibian-Gorotnichenko regression coefficients, nor the 2-year, 3-year, and 4-year cross-sectional dispersions. Alternatively, you could have overconfidence, which is basically the forecasters think that they know more, that their signals are more precise than they truly are, which is governed by this parameter phi. It's basically the ratio of that gamma bar over the gamma. And basically, if it's greater than 1, so 1 again recovers the baseline model with rational beliefs. If it's greater than 1, it means that the forecasters are overconfident. Okay, if it's less than 1, they're underconfident. So overconfidence also helps to fix both of these moments. So you could pick your favorite behavioral friction. Either one of them will be will essentially allow the model to fit the data better. The error between the moments in the model and in the data will be going down as you crank up the diagnostic expectations, or as you make people more overconfident. Okay, so you don't want to make them too overconfident. There's sort of an intermediate value that minimizes the model, that maximizes the model fit. Here you want to go to 0.8, which is exactly the value that the literature has proposed. But interestingly, all of the improvement comes from the 1-year horizon, so it leaves the long run moments unaffected. So you get this interesting dichotomy between behavioral frictions that are helpful for the 1-year forecasts. The learning about the long run mean intuitively should be about the long run, and indeed is helpful for matching these moments about the long run forecasts. Okay, so I think I'm just about at my time limit. Let me conclude. So we propose a Bayesian learning model of house price appreciation that goes, we think, a long way towards accounting for patterns of house price growth forecasts. And then certainly about the long run mean is sort of the key mechanism behind the success of the model. And then overconfidence or diagnostic expectations can help shape the short run, a couple of short run moments. In terms of disagreement, it's really mostly about prior heterogeneity. There's a lot more about this in the paper, but basically signal heterogeneity can only go so far, especially in a rational model. And then I thought, the micro data support a learning story. We have a few different ways of checking that. And then I think one thing to take away more generally about forecasting and about learning from forecasts about the underlying data generating processes of our time series that we're interested in is that it's really important to have both this cross-section of forecasts as well as the term structure of forecasts, because in special cases of the model where we say we either only have the 1-year forecast or we only have the consensus forecast and not the panel, we show that you get very different inference, right? Your inference is wrong. And so that's sort of, I think, sort of an interesting takeaway for in other contexts as well. And then we think it would be interesting to study, apply this model to other settings outside of real estate, macro or financial time series forecasts. Happy to take a few more questions. I know there are a couple of questions in the chat.
Thank you so much, Stijn. Yeah, so let's open the floor for questions. There's another one by Kundan. Maybe you want to unmute yourself?
Yeah, hi. So if I look at your model specification at the beginning, the long run mean, you have the uniform prior on that, and then the X, which is the latent variable. The persistence parameter there is fixed. And I'm wondering if you allow some time variation in that persistence parameter, that may help you in resolving some of the issues with the short run forecast. Because if you are imposing time invariant persistence, basically it's taking a look at the overall data set, and that may create issues with very short run forecasts.
Yeah, it's an interesting thought. I think there is a paper by Alfrozi and Kwan et al. That sort of thinks about this persistence being potentially different at different horizons. It's a very non-standard time series model, but that doesn't mean that it couldn't be what people have in mind when they make these forecasts. Now, more generally, we spent a lot of time in the paper thinking about this persistence parameter because it's such a prominent parameter in this Nakamura, Steinson, and Farmer paper, and so it's true that when people have biased beliefs about the persistence of the state. So let's say the state has a persistence of 0.7, but we all think it has a persistence of 0.9. Then that could actually help, because now a signal comes in. We're going to revise our forecasts a lot, potentially overdo it. That's going to generate this negative Koibian-Grotnichenko regression coefficient. So that's interesting, and I think that's sort of a new finding that mechanism can also generate that. The problem is that when we all have too much persistence about the state, then we're going to overreact to past house price growth. And in the data, we see the exact opposite. So our argument is that that mechanism of being either upward or having either upward or biased beliefs about the persistence parameter ultimately cannot account for the data. But I think what you have in mind is interesting. Remember, in our model, the posteriors about the persistence are individual specific. They are changing over time, but they're not changing across horizons, which is, I think, what you have in mind. And again, that means sort of you need to deviate from an AR1 structure. And again, it's possible that that's a reasonable thing to do. We have not explored that.
Thank you.
Any other questions? So Stijn, I had one remaining questions, but for the sake of you know, giving people time, I'll ask it in a minute. But before we finish, I wanted to talk to you about our upcoming seminar. We're going to have on June 5th at the same time. I'm Rita Kolka from Warwick, presenting Under the Neighborhood, Understanding Interactions Among Zoning Regulations. And again, we have a little bit more time for questions in case you want to stick around. And Stijn, my question was, I think that comment you gave at the beginning when you were comparing the persistence of growth between the housing market and stocks, for example, that it was interesting. And I was wondering whether, you know, that if people had specific experience at forecasting stocks, they could be just equating both markets. And if that is something that, if you've looked at specific experiences in LinkedIn, you mentioned in the LinkedIn data, you mentioned you looked at years of experience, but I wonder whether you can see in the data and the way you access it, specific experience on forecasting in other markets, and whether they're just extrapolating what they learn in other markets to the housing market.
Yeah, it's an interesting thought. Because we do know the forecasters by name. Now, I think the problem is we would need to know the forecasters by name in other forecast data sets as well, right? So let's say if you make stock return forecasts in another survey that's completely separate from this survey, do I see you by name as well, and can I match these names? I know on Bloomberg, there is some forecast data for financial time series by name. So this is not hopeless, but I think it's going to be hard to find overlap, because also I think the forecasters in this data set are different people from the ones that forecast stocks, right? These are all real estate people. They're construction company people. They're consultants of CBRE and JLL and those type of places. It's not the Goldman Sachs people that are forecasting the stock market that are also in this forecast.
Because that's the type of people that I was thinking. If you could compare people who are more connected to the development, construction, and investment in real estate versus those that are just looking at it as
my sense is, Luis,
portfolio of financial instruments.
Right. My sense from looking at these people is that they're all real estate people. You know, they're not sort of the Goldman Sachs chief economist that is making 500 other forecasts for all sorts of other series. If it's a Goldman Sachs person, it's a real estate Goldman Sachs person.
Okay. So that comparison would be interesting if you were able to do it. I think Amin has a question.
Yeah, and apologies if it's a non sequitur, but I was wondering whether in some sense there is the possibility of extracting an orthogonal signal about, for instance, your forecast, Stijn, to sort of get a sense of whether there's an innovation in forecast that is there private information that we can back out from these forecasts, or are they, in some sense, is the model observationally equivalent to a model where every forecaster relies on the same time series of information?
No, definitely. I mean, we can see the time series of forecasts, and we can see the revisions at the individual level from one quarter to the next in how these forecasts are changing. And then through the lens of the model, we can extract essentially what is the news that these forecasters must have had in order to revise their forecast in the way that they did. Right, so we under the null of the model, we could absolutely do that, and then what we will see is that there's a lot of heterogeneity in the signals that these forecasters are using. right? So I think that's true. And so I think they all have their own sources. Now, of course, that's where it ends. There's not much more we can say. It's not like we can say Stijn was using GDP data and Amin was using Florida house price data when he was making his national forecast. That we will never know. But what we could back out the amount of information in these forecasts through the lens of the model. And how much heterogeneity there is. In fact, that's what the model does. That's how the model estimates the dispersion in signals.
Thank you so much. And could you build a super forecast in the sense of combining these individual forecasts to improve on the precision of the individual forecasts?
Potentially. I could tell you as sort of an empirical matter that you could look at the best 5 forecasters in past surveys and see whether the forecast of the best 5 forecasters is a better forecast. I've tried this as an empirical matter. This is sort of separate from the paper I presented, just sort of in my own personal forecast. That's a model. That's a mental model. Let me just look at the 5 most precise forecasters and average their forecast. And that forecast does not do very well in the sense that you can find machine learning models that outperform that forecast.
Thanks.
So I'm a little skeptical that there's going to be a ton of information. In general, one thing I learned from this project is it's in general very difficult to forecast house price growth. And I think the reason it's so difficult is because the time series is persistent. And so the forecasting is all about predicting the turning points. And that's just inherently a very difficult problem.
Thanks.
Stijn, there's no asymmetry between in the initial rational form of the model between times of decline and growth of prices, right? There's no. Is there any asymmetry? It wasn't clear to me if when you add the behavioral components, if there's any asymmetry there between those two moments of the cycle.
It's certainly not obvious that there is, even, right? Because what these behavioral frictions are doing is essentially in the overconfidence, you're responding more to news, but it doesn't matter whether the news is good news or bad news. You're going to respond more in both cases. And the same with the diagnostic expectations, you're overweighing more recent experiences. And again, you're overweighing them whether they're good or bad news. So there's nothing about these specific behavioral frictions that's asymmetric in nature.
Yeah, and these stylized facts that you listed at the beginning, they're also symmetrical. There's none that is classified, because I thought that there would be. I'm not very familiar with the behavioral finance, I guess, literature, but I thought there might be differences in the way the literature has identified the reaction between growth and decline, and I wonder whether that would further. I mean, I don't know how much you can improve the prediction, and that's probably another paper, but I wonder if that's something that could improve it.
Yeah, nothing immediately comes to mind.
Okay. All right, if there aren't any other questions, Stijn, thank you so much for joining us again. We'll have the recording available probably tomorrow.
Thanks, Luis. Thanks for having me.
Thank you so much, and hope to see you next week around DC.
See you all in DC.
All right, bye-bye.